Well, welcome to this month's Lunch and Learn webinar from Yugabyte. It is fractionally before 12:30 in the UK, so I think we're starting 30 seconds early. That makes it about 1:30 in Europe, and by my calculation, 6 p.m. in India. Again, it's fantastic to have so many people joining. We ran this similar session last month, and we got lots of good interaction. So if you have any questions that come up as we're going through the material, then please be sure to post them in the chat, and we will pick them up as soon as we can. So let's get started. I think actually a good place to start when talking about databases, interestingly, is the application layer. Most organizations have taken a look at their application layer and now re-engineering their application layer to take advantage of containerization and Kubernetes, and are really running their applications in a very horizontally scalable cloud native manner. So say typically in Kubernetes or Docker containers and the like. So they built a wonderfully resilient, easily scalable application layer. But what people are realizing is that that beautifully scalable application layer is all pointing back to a monolithic, rather old-fashioned database, typically connecting to Oracle or SQL Server or the like. That monolithic database that's sitting in the background there, if you want to scale it up, if you've got increased workload, then you need to vertically scale the database. There's no ability to horizontally scale in any way. And additionally, if you're worried about resilience and high availability, what people typically do is build a second database kind of alongside the first database, or maybe in a HA, disaster recovery data center, continuously copy the data over to the backup database, and in the event of a failure, will move the application traffic over to that backup or HA database. In a lot of ways, these architectures point back to the kind of 1990s, early 2000s. In a lot of ways, quite an old-fashioned architecture. So that is why people are now looking at what is called distributed SQL. Distributed SQL brings all of the benefits of cloud-native, containerized applications, but it brings it to the database layer. So a distributed database, by its nature, is distributed. Typically, there's a minimum of 3 nodes that are collaborating in order to serve the database. If you need to scale up the database for any reason, if you're anticipating additional load, you simply add more nodes. If you have cyclical workload and you need to reduce the capacity of the database back down again, you simply take nodes away. So in this way, the database is horizontally scalable, adding nodes, removing nodes, and really just responding to the overall traffic that you're pushing through the database. Oftentimes, people run multiple nodes. I'm showing a 9-node cluster here, which is often distributed across multiple regions, be they cloud regions, Frankfurt, London, Rome, for example, or potentially more diverse than that. Interestingly, those different regions could actually be spread across multiple cloud providers, or even a combination of public cloud and on-premise. So therefore offering a truly hybrid multi-cloud operational environment. In this setup, let's say you lose a node, then the database just keeps running. It's resilient to any node failure. The data is replicated across multiple nodes within the cluster, and we use something called a raft consensus algorithm to make sure that data is secure and committed and safely stored before we acknowledge any change. So in this way, a node failure has no impact on the database. Even in a more extreme manner, you may lose an entire region. So if we're running that database that I mentioned across Rome, Frankfurt and London, and let's say you lost connectivity with the Rome cloud region for some reason, again, the database, the Yugabyte distributed SQL database continues to run. All we need is a majority of nodes. And in this setup here, despite the fact we've lost one node in one region and an entire region, we've still got five nodes running, which is a majority. So the database can continue to operate. I've got an interesting question actually here. So as I say, please keep your questions streaming in onto the chat. I'm not sure if everybody can see that, but I can certainly see the questions coming in. And there's a question here that says, what's the difference between a distributed SQL Yugabyte database or a NoSQL database like Couch or CouchDB or Cassandra? And that's a very good question. So the key difference, the essential difference between distributed SQL and what people call NoSQL is all about transactional integrity. So Yugabyte provides a Postgres SQL compatible API. So if you've got a Postgres application speaking Postgres, it can work with Yugabyte. And crucially, we honor all of the transactional semantics that you get with a traditional RDBMS like Postgres or like Oracle. So it is 100% ACID compliant. There's no kind of vagueness about that at all. ACID compliant, strongly consistent, transactionally integral, despite the fact the database is working across multiple availability zones and multiple regions. It's all based upon an algorithm called the Raft consensus algorithm. I won't go into that now. It's very interesting reading. So if you look that up, you will learn about how Yugabyte is able to ensure transactional integrity. So thank you for that question. It's quite timely, actually. Anyway, moving on. So we're showing here how the Yugabyte database is resilient to change, despite the fact that we've lost an entire region or an additional node within a third region. Oftentimes, people run these distributed databases across geographically diverse infrastructure. So I'm showing my 9-node cluster here, running across a combination of the US, Europe, and Asia Pac. This can be for many reasons. People may want just a globally distributed database because they're serving traffic across the entire world, and they want to make sure they've got low latency access to the database from any of these different diverse regions. Another reason may be that you have regulatory requirements. So you require a globally consistent database, but for regulatory reasons, you must physically store data within certain geographies, what people refer to as data sovereignty. So European data, because of GDPR, stored on nodes that are within the European zone, US data over in US, California data maybe specifically in California, possibly, and Asia Pac data over in Asia Pac. In this setup, again, we have a globally consistent, transactionally integral, ACID compliant database, but we're ensuring the data is stored in the particular regions within that setup. So it's interesting to look at the technology, and we've talked about how the architecture is a much more modern architecture and really is comparable in a lot of ways with what people have been doing on the application layer. But it's also very, very important to think about the business impact. What is the business benefit of running databases in a cloud-native distributed SQL environment? And I've called out here just three of our customers that have been running Yugabyte and distributed SQL for quite some time now. And it's interesting just to look at the benefits that they're getting. So Kroger, very large retail operation, primarily in North America. So without Yugabyte, Kroger wasn't able to run its shopping list service with resilience and scalability across all of the different regions that they require in North America, crucially with single-digit latency, single-digit millisecond latency, I should say there. So any interaction with the database is going through in 3, 5, 8 millisecond type of response times. I think, as we all know, especially within a retail context, it's incredibly important for applications and websites to be very, very responsive. And this is a key driver for Kroger. Very low latency with the database infrastructure spread across the US for resilience and in order to ensure that low latency. Slightly different use case is General Motors. So General Motors use Yugabyte as the repository, the database that receives all of their vehicle telemetry data for their connected car infrastructure. So I think pretty much every General Motors car that you buy, probably worldwide, but certainly in North America, is generating huge amounts of telemetry data. That's all working its way through an infrastructure and ultimately lands in a Yugabyte database. There are two key drivers here, interestingly. The first actually is more about scalability. So scaling the database was really being driven by just the huge volume, just lots of cars being purchased, more cars coming onto the system. And they were finding with the prior infrastructure that they were spending more time adding capacity than they were operating the infrastructure. So Yugabyte really helps with that. And then the second key benefit is actually uptime and availability. The resilience of this system is incredibly important. The E911 service, the emergency services where they need to know exactly the location of the car. These types of services are critical, and you can't afford for the database to be down when the emergency authorities are trying to find out the location of an accident or the same. And then the third example that I wanted to share is Plume. If you're in the Wi-Fi telco space, I'm sure you'll be very familiar with Plume. They sell to many, if not most, of the ISPs and telcos around the world. And they provide a platform that collects metrics from the Wi-Fi platforms that the ISPs are operating, and then offer a kind of troubleshooting and management environment for those Wi-Fi platforms. The interesting thing about Plume is it's a SaaS offering, so it's a global database, but it's crucially important for the data to be specifically stored within any of those geographic environments. It's kind of linked to that latter scenario that I was talking about, where the data is geographically distributed. So about halfway through now by my clock. So keep your questions coming. I can see there's one question about how is the data spread? How is the data spread out across a Yugabyte database? That's definitely an interesting question. I'll come to that in a second. Because what I would like to do is to move on to a demonstration. Now, as I say, we ran this lunch and learn session last month as well. And last month, we focused on scaling out a database. This month, I wanted to focus on just looking at the application or the database from an application perspective. So what I'm showing you here is a demo that we've put together. It's emulating or simulating an international bookstore. I've got my mobile app here. It's got a few extended features. I can pretend to be in different locations. As you know, at the moment, as you can see on the drop down there, I'm pretending to be in Los Angeles. And as we move through the demonstration, I'm going to move the location of my phone so I can show you how all of the connectivity works. What we've got on the right-hand side here is a simulation, already a kind of a spyglass or an X-ray of what's happening on the database. So my Yugabyte bookstore is connected to a Yugabyte database. The three green dots are the nodes of my 3-node database setup. All of them are over in Western US, so it's kind of single region, multi-availability zone cluster, and the mobile app, as you can see, is in Los Angeles. So if I click around on the application here, I'm just looking at the inventory, and let's just zoom in a little bit and see what we're getting at in terms of latency. So you can see I'm querying the product catalog, getting really low latency, so 2 milliseconds. Execution time on the database is 1.3 milliseconds, very fast, and the overall latency is of the order of 2 milliseconds. I can add that book to my cart, click into the shopping cart, actually hit buy, and purchase a book. So I've moved from doing select type operations through to actual transactions, insert type statements, and again, nice and fast, 7 milliseconds for inserting data. These are the kinds of latency that we're talking about that Kroger required. Now, I'm going to move my application. I'm going to move it over to Washington. The database is still over on the West Coast. And as you can see, I'm clicking around. It's a little less responsive. There is distance between Washington and the West Coast. And actually, I've just moved my mobile app all the way over to London. And you can see we're beginning to get latency. Now, why is that? The database is performing just as fast. It's all due to physics. There is the speed of light problem. Much as we'd like to go faster than the speed of light, we can't, and therefore it just takes some time for the traffic to move or to get from London all the way over to the West Coast. And you can see here, if you look at on the right hand side there, we've got a latency of around about 150 milliseconds, 144 milliseconds, that type of latency, as we're interacting with the database from London. Now, Yugabyte is a distributed database. There's lots of things that we can do. And I'm going to talk about a couple of different topologies. So the first topology is where we establish a multi-region database, read-write cluster, and we put read replicas essentially dotted around the world. One of those read replicas is in London. And now, as I'm scrolling around, you can see on the right-hand side there that my selects are back down to the 3 milliseconds. Simple reason for that. My reads are going against the read replica. It's nice and close, and it's highly responsive. If I buy a book, I'll be going against the database, the read-write cluster, which is still in North America. So we'll be back up to the sort of 170, 150, or this one's 200, 170 milliseconds. And that might be okay. You know, you might have an application that is very, very read oriented. It's more about reading. So I would like to deploy a topology which focuses on optimizing the consistent reads. But I'm okay. I'm happy for the read-write traffic to be over, you know, around about 140, 150 milliseconds, something like that. Now, if I were to move my my client, my mobile app down to Mumbai, could well be a different picture. So I'm clicking around, and as you saw there, you could see that the read traffic was rapid, but the write traffic is just kind of tipped over into something that we're not happy with. So we're going to look at a different topology here. This is the kind of topology where we're spreading the data around in more of a geo-distributed manner. So it's still a globally consistent database, but I've changed the topology, and I'm now using a topology, or pointing to a database that is using a topology that is distributing the data geographically. So I've got all of my customer data for the India, you know, South Asia segment of my customer base is all stored and manipulated on the Mumbai nodes. European data is in the European nodes, etc. Now, when I click around, you can see that I'm clicking. I've got a 2, maybe 4 millisecond latency. I add the book to my cart. I go and buy the book. And despite the fact it's an insert transaction, because the database is geographically distributed now, and all of the India data is in the India nodes, now I've got my actual purchase, you know, insert type transactions going through in, you know, 2, maybe 4, 5 milliseconds, something like that. So very, very, very fast. So what we've done here is we've looked at a range of different topologies. Just going to stop my screen sharing there. We've looked at a range of different topologies. There isn't really a one size fits all. You know, the interesting thing about Yugabyte is it gives you a range of different topologies, and it's really a case of looking at your use case, working out what is the distributed nature of my data. You know, what's the sort of profile of the traffic in terms of, am I read heavy? Have I got an even number of reads and writes? And then what latency am I interested in trying to achieve? In that way, we can help you design the most optimal topology and hit your your business requirements. Now, I said there's a couple of other questions come in actually. So the question that I referenced earlier that came in was asking about how is the data spread out? Quite a simple question, really. And actually, fortunately, a pretty simple answer. So if we were to return to the simple that first cluster we looked at, where we had a multi-node cluster that's just a simple read-write cluster, not worrying about read replicas and all those sorts of things, then by default, Yugabyte automatically shards all of the data and spreads it evenly across all of the nodes of your cluster. We actually base this on a hash of the primary key, which means that the data is very evenly spread out and you get an even amount of kind of work and of storage spread across all of the nodes. So by default, that's what we do. And in many, if not most situations, you as a DBA or an application developer don't need to worry about it. And Yugabyte just automatically handles it for you. As I mentioned earlier, though, you know, you've always got options with Yugabyte. So if you want to force data to be stored in different physical locations, and this gets into the sort of third model that we were looking at, then you can instruct Yugabyte based upon normally a column within the database, and you can instruct Yugabyte to look at that column and then cause the data, the rows of the table, to be placed or stored within specific nodes in the cluster. So you've got complete flexibility. It's down to you as a DBA or as an application developer to say, I'm happy with uniform, even distribution of the data across my cluster, and I'm just going to worry about whether I want the cluster to be spread across multiple zones or multiple regions, or you can get into a little bit more detail. Now, there's one, I've just got time. I want to make sure that I finish on time, but there's a third question that's just come in, which is asking about how do you connect? If you've got it says, how do you connect to the Yugabyte cluster, and how do you make sure that the connections are spread out as well? I think that's probably talking about, or it's trying to get at, if you've got a multi-node cluster and you've got an application, what do you connect to? Is there a primary, is there some kind of master kind of slave type of operation, something like that? So it's actually quite a good question. Often the simplest questions are the most insightful, really. So with the Yugabyte cluster, notwithstanding read replicas, every node is a peer. So in a normal Yugabyte cluster, every node is a peer. We don't talk in terms of masters and slaves and leaders and followers and things like that. At the node level, every node is a peer. So an application can connect to any one node. That node can serve both read and write traffic evenly, no matter where the physical data is stored on the cluster. So very easy. Different application connections can connect to different nodes. And as we mentioned at the beginning, the database is strongly consistent. So if a piece of data has been written by an application at one node, and then instantaneously or just fractionally after that node has taken the update, someone else tries to read that data, you are guaranteed to get the up-to-date data. None of this eventual consistency problem that NoSQL databases suffer from. So that's guaranteed. And in the CAP theorem, I should point out we're a consistent and partition-tolerant database. But you may want to be able to spread your connections across a database. And really, just quickly, there are two very easy ways to do that. You can simply put a load balancer in front of the database, and in that way, the applications spread their load using the load balancer, or we have a smart driver which will do that automatically for you. So thank you for that question as well. So pretty much coming to the end now, just a couple of minutes before the stop time. So just quickly in summary, Yugabyte is a strongly consistent cloud-native database, leveraging this whole movement towards distributed SQL. The primary benefits are horizontal scalability, leveraging the fact that it's a distributed multi-node database. You can easily scale by adding nodes. You typically place those nodes in different failure zones, and therefore you get architected or built-in resilience. They're the two primary benefits of a distributed SQL database. And then the third kind of knock-on benefit is you can spread your data across geographically diverse regions, either for improved or reduced latency, or for regulatory requirements. So thank you very much. Thank you for tuning in. Really appreciate your time and look forward to the next session. Thank you.